What I want to present is our work on stream processing mostly. So I'll give a quick overview of the group and then really focus on one aspect today here. So I'm Tilmann Rabl, I'm professor at HBI, and this is the group. And you can see in the center, there's Fonda. So this is Raphael here, and he's our Fonda PhD student. And what we're doing is really, well, data engineering systems. And if I talk about data engineering systems, I really think about database systems in the generic sense of the topic. So, and this means it's all systems research in different, well, directions. And one of the core directions that we're looking at right now is stream processing. And here I have like some of the publications that we recently did. So we mostly publish at SIGMOD and VLDB, and then some side conferences as this. And as I said, stream processing, this will be the focus. So here I'll put an emphasis and you will see some of the recent work. And this is really also what we're looking at in Fonda. So our work is on monitoring of data analysis workflows. And the monitoring is done in a streaming fashion. And so we're looking in the work package at how to do the streaming really in an efficient way. And here in this presentation, I'll show you some of the techniques that we're going to use in Fonda as well. Besides that, we're also working on like regular database management, so joins, etc. And a lot of this also on modern hardware. I'll touch on this a bit. Then completely different, not completely different, but like a slightly different direction is machine learning systems. And also a lot of my work is centering out around benchmarking. And so this will be in team 5 of relevance in Fonda. And so the approach, how we do this is, in our group really is somewhat like this. So we have a certain application scenario that we're looking at. And from that, we're going to develop some benchmarks. And this means really at some point, it might be a real standardized benchmark. So we help with the TPC XBB, for example. So the Transaction Processing Performance Council is kind of the standardization organization in database benchmarking. And some of our benchmarks have been picked up there. And with these benchmarks, and sometimes it's more like evaluations or evaluation rules, let's say, we're actually benchmarking a lot. And so this is also or let's say the next iteration in a lot of our research. So looking at what do current systems do? It's like, what do they provide? And where are the bottlenecks? And especially where are the bottlenecks if we look at a certain application? And then we try to extend existing systems and sometimes exploiting new hardware. So hardware constantly changes, so there's always something to do here. And if we see that existing systems or using new hardware on existing systems doesn't really work, we're going to go over to new systems development. And well, sometimes we even get stuck somewhere in the pipeline. So meaning sometimes it's all about the benchmarking, and then that's the paper, and there's not much more to do than there. And as I said, today, it's really the focus is on stream processing. So what is stream processing? So typically you have some kind of interesting data stream. So this might be your nice scientific data stream or experiment like CERN, or you have a car, an autonomous car where you have lots and lots of sensors, or you have a Twitter feed where you want to do some cool data analysis. And the idea is that you have a continuous data set. So it's not something like I'm not looking at the Twitter feed last year or something, or the autonomous car data that was processed or that was generated 2 years ago. I want to see what's happening right now. So I have to send this information, this data stream into a stream processor. I pose certain questions to it, and then I get a result. And the result is also continuous. So it's not one result, it's not 5 or 42. It's a series of results. And that will then go into a machine learning system, into a dashboard, or into another stream processor. Or we might even store it, of course. And there's a couple of challenges Potentially, the data set is unlimited, so we don't know when it stops. We might have many different queries on the same kind of stream, and we want to have low latency and continuous results. And typical systems would be Spark Streaming, Apache Flink, which was developed at TU Berlin, and Apache Storm. And so if we look one step deeper or more inside, let's see, typically internally, this looks something like this. You have multiple data streams, one or two or multiple, as I said. So in many cases, it's just one. I mean, to make it more interesting here, I have two data streams that go into the source operator of a stream processor. Then we might have different kind of operations on the stream. So, and you can see we have these individual events in there. And so this would be individual sensor readings or something like that, or individual tweets by Trump that we want to analyze. And then we might have some control events that tell our stream processor what to do next or how to change itself or to say, for example, store something. And then we might have stateless operators. So something like a filter. So we just want to, well, maybe filter out all Trump's tweets, or we want to do something else. Or we might have an aggregation, and this is a stateful operator. And in an aggregation, for example, we want to combine everything. We want to count, we want to average and things like that. And then we can join multiple streams. And in the end, we send this to a sink where we have our result stream. And of course, there's many different kind of operations, but so these are kind of the basic operations that we would look at. And one of the first things that we looked at, I mean, we looked at many things, but one of the things where we really found some nice improvements is aggregations. And typically, the way you process this, of course, you have to look at this. If you do an aggregation like an average or a min-max, you cannot do this for the whole stream. You have to split it up into smaller parts and then take this sub part of the stream. And this you do by windows. So you have to somehow window the stream. And a simple windowing would be a tumbling window. So you're just cutting up the stream into, say, equal sized blocks. And something more elaborate is, say, for example, a sliding window. And so if we look at this kind of raw stream, so you have these individual events, they have a value, then a sliding window on top of that might look something like this. So we have up to 9 values, we have some holes in the stream. And then what we, for example, do is an aggregation. So we want to sum up the values inside each of these windows. And so typically what a current stream processor does, it just uses an individual buffer per window. So it will, each of these yellow things will be a buffer, and then we're just copying all of the events that fit into this window over and over and over. And the problem, I mean, in general, this is fine, right? So in my example here, I might have 3 copies of each event, or not might, I will have 3 copies of each event. And you can say, well, this is sort of okay. But what if I have a windowing that has like a 1 hour length, and I'm moving it by second? So I want to have a dashboard which looks at the last hour, but I want to have it updated every second. Then, of course, I have 3,600 copies of each event. And all of a sudden, this kind of gets cumbersome to keep in memory, especially if the stream is really fast. So what can we do? We can do something that we call stream slicing. So rather than copying everything into a buffer, we're slicing up the stream. And then we can do partial aggregates for these slices. And this depends on if we can decompose the aggregates or no. So decompose means, say, for example, an average we can decompose into a count and a sum. And the count and the sum, we can just sum up, basically, right? And then we can, by this, we can create the aggregate out of the partial aggregates. Something like a median, we cannot decompose, and here we always need the full buffer. Still, we don't have to copy, we can just reuse these slices. So using, say, for example, the sum, we can aggregate this, calculate the partial aggregates, and we do this for all individual slices. And then in the end, we have to do a lot less computation. So in order to, say, for example, compute this, I don't remember which one I have. So in order to compute this window, I just need to use the 3 partial aggregates. So in the end, I will have a lot less memory used, and I will have a lot less computation used. So this will become much faster, and it becomes really significantly faster. So this is like compared to a basic setup. So the buckets approach, which is something that would you do in Flink, you can get up to 3 orders of magnitude speed improvement or performance improvement. And this doesn't only work for sliding windows, it also works for session windows, which are even more complex. And well, I'll send you to the papers for details here. So, but this we thought is really nice. And the cool thing is we can also do this in a distributed setup. So rather than doing everything in a centralized stream processor, we can also look at a setup that's highly distributed, say data analysis workflow with a lot of individual parts that need to be monitored. So now we might have, I don't know if these are really thousands of individual parts that we need to monitor, then there will be multiple network hops. And in the end, we're going to send all of the data to some central instance where we do the monitoring. And if we want to do these aggregations, we can, if they're decomposable, we can already pre-compute them in these network hubs. So the idea is that we do the same kind of windowing. If we have similar aggregations or we have the same aggregations, we can do the same thing that we did and reduce the amount of data that is shipped to the cloud data center or to the central monitor a lot. So in the end, we can scale to even much higher numbers of events that we can process and much higher number of results. And so we utilize compute resources in the intermediate nodes, and we minimize the data transfer. And so what we're working on this here right now is then even to optimize this across different kind of aggregations. And so that's kind of the aggregation part. Now, at the same time, especially if we look at a monitoring setup, we can see on the one hand, not all of the monitoring queries are really run forever. So one of the major assumptions in systems like Flink is that this is like you have your query once and it's going to run until the end of time. So basically, deployment can take a long time because in the end, it will pay off because you're just running this forever. And so that's, of course, that's not necessarily true, right? So sometimes, especially in monitoring, I would want to look at different kind of queries, right? I want to look at different kind of aspects. I might want to have different aggregations. So that's one thing. And some queries might just be like, I just want to see, oh, it's not really what I was looking at. So let me try something else. So I want to be able to just deploy this quickly. And at the same time, especially in monitoring, a lot of the queries look really similar. So it's not like I'm doing a generalized mapper function here, but I really have to select, project, join, aggregate type of query, and all of them look more or less the same. So why don't we reuse this? And this is kind of another work that we did that was, I think, quite nice. And so the idea is that we do multi-query processing in a stream processor. So we build a topology for standard queries. So select, project, join, window, aggregate. And then we have our data stream, but at the same time, we might also have a query stream. So we can, rather than just sending a data stream, we can also query or send the queries in as a stream and basically say, okay, this query is added, this query is deleted, and then have a result stream where we split up, or where in the stream we also say, okay, this query or this result is for this query. So we get a result of mixture of, I should have colored this, of query and result in the end. And so then we, of course, we can add, in order to do so, we add query indexes to the tuples. So we send the tuples in, or the events in, and we say, okay, this event belongs to this query or to these queries. And this way we can keep an eye on how to actually process, or what to process how. And then if we evaluate the queries as late as possible, we don't have to do any duplicate computation. So this, as I said, works quite nicely. We can optimize dynamically. And in the end, again, we get orders of magnitude throughput improvement. We pay by a little bit of latency. So of course, if we process multiple queries at the time, it will be a bit more costly, but it gets much more efficient. So it's basically has a similar single node performance. So here you can see this is A stream. So if Flink does 1 million records per second, A stream is like 0.98 records per second. But then we can scale up to hundreds of queries at the same time, and then the total query throughput will be much, much higher. So I'll have to speed up a bit to stay in time. So another aspect that we were looking at, and I already said that we are also interested in modern hardware, or in how to use hardware efficiently. And so if you look again at something like Flink, what it does, it has this interpretation-based processing, meaning, and it's like a tuple at a time pull-based mechanism. So you have for each operator, as I showed you earlier, you have a single instance in your system, and the data will be given from one operator to the next. Even if you have it on a single node, there will be a lot of function call overhead on this node. So, and this is highly costly in terms of cache misses, in terms of function call overheads and things like that. So an alternative strategy is to really tightly pack this and compile it into a single program that can be run much more efficiently. And so this is what we did. And here you can see kind of the hard-coded version. We also have a more efficient, or not a more efficient, more generic version that has similar performance. And what we can see is that if we have a throughput of 1 million records per second, if we're looking at something like Flink, we might get up to like 6 million records per second. If we look at the leftmost picture here, in Flink for a YSB, so the Yahoo streaming benchmark on a single node. And if we somehow, or if we do this natively in Java, so we're not using all of the overhead that Flink produces, because Flink is a generic stream processor, then we can get up to 24 million, but we still have all this function call overhead and everything. And so then we can actually optimize this and run it close to the hardware speed using C++ by compiling this. So, and if we compile, we get again, well, not completely 2 orders of magnitude, but almost 2 orders of magnitude performance improvement. And this across many different types of workloads. And well, this is really as close to what the hardware can give you. So we're at almost at memory bandwidth in terms of stream processing here. So I think it's as a final part, I want to shift gears a bit and look at more realistic stream processing deployments. So, I mean, right now I just looked at the stream processor, and then we have the data stream that goes into the stream processor, but that's not really what a typical system looks like, because the stream processor is usually something like Flink is pull-based. So it will pull data from a source, and the data stream is push-based. So the data stream just arrives as it can, and the stream processor has a problem here. So in order to be fault-tolerant and reliable, it usually uses something like a message broker. So the data goes into a message broker, there we'll have some ordering, we'll have some reliability, and then the stream processor really processes it. So it orchestrates the event flow and has like this fault tolerance and replay functionality. And often it's a bottleneck. So typically this in today's system, this looks something like this. We have a producer that sends the data to the broker, and the broker stores this information and partitions this. So we have different kind of topics, and then the consumer can read from these topics. And these topics also allow us to parallelize inside the stream processor. And the communication is message-based, and we have a broker-centric data transfer. We have some kind of append-only log, or disk storage, so some storage service. So it might be replication, might be directly on the disk. And well, typically, as I said today, this is often a bottleneck. So, but there's new technology on the horizon that we can use. And one is non-volatile memory, which is byte addressable, non-volatile RAM, basically. It's 10 times higher, has a 10 times higher density than RAM, has a similar performance, not as fast as RAM, but similar. And on the other hand, we have remote direct memory access, which is much faster way of accessing or of data transfer across the network, and by directly accessing memory on another node. So now we can, of course, nicely combine the two. And so this is what we did in rethinking message brokers on NVM and RDMA. So this was actually also a submission to the student research competition where it got the, at Sigmod, where it got the second place. And well, currently we're working on the full paper. So the idea here is that the data transfer is really done using RDMA, and the broker is only focused on the coordination. So the overhead here is much less. And the storage is done in non-volatile memory or persistent memory. And this way, again, the overhead on the broker is much less because we can directly write into the memory rather than going through the CPU using the network stack. And the consumer can directly read this. And the nice thing also is we can place the broker either directly at the producer or the consumer and have basic almost zero CPU overhead here and have the data directly where we want it. And it's persistent because non-volatile memory is persistent. So this all, again, gives us quite a nice performance improvement if we do so. And with that, perfectly in time, I would say thank you very much. So I talked about the stream processing, gave you a bit of an overview of what it means, and then looked at distributed aggregation, multi-query processing, and hardware conscious processing, which are the kind of topics that we really want to bring in Fonda. Thank you.